is the framework of the also is D0604 physics 074300 technical physics 6D0 7100 thermal power engineering, D07108 electric power engineering, 6D01 6D07300 standardization and certification, 8D0530 nuclear boosting, 8D201 radio engineering, electronics and telecommunications, the Kazakh National University. A meeting is held on December 22, 2025 with a quorum present. All 8 members of the Education Council according to the approved list. The quorum is confirmed. Attendance list.
Смотрите, я ничего не слышу. Очень плохо идет. Остальные слышат, да?
Вот плохо слышно.
Мне тоже плохо слышно было, да.
Прерывисто идет, прерывисто. У вас что-то с микрофоном не так.
Сейчас слышно теперь?
Да, сейчас слышно.
Слышно, да? Хорошо.
Да, сейчас лучше.
Attendance list. Vice Chairman, Medical Science Professor, Mikhail Kunduz, Scientific Secretary, Candidate of Physical Mathematical Science, Associate Professor, Members of the Dissertation Council, Doctor of PhD, Mathematical Sciences,
Да.
Professor.
То есть у вас микрофон не настроен?
Либо микрофон, либо из-за связи. Там...
Связь, кажется.
Нет, связь-то нормально, мы же слышим. Мы же все слышим друг друга.
Не, у них связь плохая.
Не, у них именно, да, может быть.
А, может у них, да. Потому что у нас все нормально, мы друг друга слышим.
А сейчас тоже не слышите нас? Раз, два, три.
Да, сейчас мы слышим.
Почему по перерыву? Ну, я уже закричу.
Вот сейчас слышно.
Ага. Ахмедов Бабу Мурод, ревьюер,
Да.
доктор of physics, science, academician of the Academy of Sciences of Uzbekistan, the head of the Department of Theoretical Astrophysics, Ulugбек Astronomical Institute, Tashkent, Uzbekistan. Алдабергенов Ермек, PhD, Research Associate, Udan University, Shanghai, China. Reviewer. Abdul Jabbarov Ahmadjon, temporary member of the Dissertation Council, Doctor of Physical Mathematical Sciences, Professor Ulugбек Astronomical Institute, Tashkent, Uzbekistan. Toshmatov Bodbir, temporary member of the Dissertation Council, PhD, Professor, New Uzbekistan University, Tashkent, Uzbekistan. Tursunov Arman, temporary member of the Dissertation Council, Doctor of Physical Mathematical Sciences, Professor, Institute of Physics, Silesian University in Opava, Czech Republic. Recommendation to open the Dissertation Council meeting. Any objections? No?
No objections. No.
Okay. I declare the meeting of the Dissertation Council open. Agenda: defense of the dissertation work series of articles of Gulnara Suliyeva on the topic application of field theories to astrophysical problems for the degree of Doctor of Philosophy in the educational program 8D005306 Physics. The work was completed at the Department of Theoretical and Nuclear Physics at Al-Farabi Kazakh National University. Scientific supervisors: Bushkayev Kuantai is a Doctor of Philosophy, Professor of the Department of Theoretical and Nuclear Physics, Al-Farabi Kazakh National University, Almaty, Kazakhstan. Luongo Orlando is a Doctor of Philosophy, Professor of the Physics Division, University of Camerina, Italy. Official reviewers: Ahmedov Bobomurod is a Doctor of Physical and Mathematical Sciences, Professor, Academician of the Academy of Sciences of Uzbekistan, the head of the Department of Theoretical Astrophysics, Ulugbek Astronomical Institute, Tashkent, Uzbekistan. And Aldabergenov Yermek is PhD Research Associate of Fudan University, Shanghai, China. The dissertation, a series of articles, has been submitted for defense for the first time. All dissertation materials are available to the Dissertation Council members. Are there any comments on the agenda? If no comments, the agenda is approved.
No comment.
To familiarize the members of the Dissertation Council with the personal file of the PhD candidate, the floor is given to the Scientific Secretary Kunduz Turikhanovna.
Thank you so much. Dear members of Dissertation Council, please allow me to familiarize you with the materials on the dissertation of Gulnara Suliyeva. First document is the application addressed to the chairman of the board director of Al-Farabi Kazakh National University for acceptance and the submission of dissertation for defense. Second is abstract in the three language and the publications. Form of defense is a series of articles. Third document is the information about the doctoral student. Suliyeva Guldana was born on the 22nd August in 1999 in the Issyk Almaty region, Kazakhstan. In 2016, she entered at the Al-Farabi Kazakh National University, from which she graduated in 2020 with a degree in physics, bachelor degree. And in 2020, until 2022, she completed her master degree in physics at Al-Farabi Kazakh National University. Between 2022-2025, she completed her doctoral studies in physics also at the Al-Farabi Kazakh National University. Currently, she works as a junior researcher at the National Nanotechnology Laboratory of Open Type at Al-Farabi Kazakh National University. And the fourth document is a certified personal card of an employee of Al-Farabi Kazakh National University. And the next, a certified copy of transcript in 3 languages confirming completion of the doctoral program. Next, reviews from domestic and foreign scientific supervisors certified at the place of work. 7th document, except from the minutes of department meeting with a positive conclusion and the recommendations for the work to be defended, approved by the member of vice rector for scientific and innovation activities of Al-Farabi Kazakh National University. And the 8th document is the reviews from official reviewers certified by the reviewers' place of work. 9th document is the except from the minutes of the meeting of Academic Council of Al-Farabi Kazakh National University on approval of the dissertation topic and the scientific supervisors. And the 9th document is the order of chairman of board rector of Kazakh National University on sending the dissertation for defense. The 11th list of scientific publications certified by the scientific secretary of Al-Farabi Kazakh National University. And the 12th document is a conclusion of the local ethics commission of the university. Based on the results of dissertation work, 9 works were published, including the 4 articles in journal included in the scopes and the Web of Science. They advise 4 articles Q1 and Q2, one of which Gulnara is the first author. 4 articles in publications recommended by the Committee of Quality Assurance in the Science and Higher Education of the Ministry of Science and Higher Education of the Republic of Kazakhstan. In the materials of the international conference, 1 scientific work. And the materials submitted by Gulnara Suliyeva comply with approval rules for preparing dissertation for defense established by the Committee for Quality Assurance in the Science and Higher Education of the Republic of Kazakhstan. The dissertation work, series of articles, is eligible for defense. Thank you.
Thank you, Dr. Turikhanova. Dear colleagues, do you have any questions?
No.
No.
No questions. No, everything is clear.
Okay, thank you. If there are no questions, Gulnara Suliyeva will speak. Time limit 20 minutes.
Раз-два. Good afternoon, dear members. Good afternoon, dear members of the Dissertation Council, dear guests. The topic of my dissertation work is application of field theories to astrophysical problems. My scientific supervisors are Professor Boshkaev Kuantai and Professor Luanga Orlando. The aim of the research is theoretical analysis of gravitational effects in black hole models, including additional fields, nonlinear electromagnetic and dilaton fields. Research tasks are first to study classical effects of general relativity in the spacetime of the van regular black hole. Second, to investigate the radiative properties of accretion disks around van and the Debnikova regular black holes. And the third, to analyze circular orbits in the spacetime of dilatonic black holes with 2 scalar and 2 vector fields. The relevance of the topic is defined by the current progress in observational astrophysics, which allows us to test the predictions of gravitational theories. We know the projects like Event Horizon Telescope, LIGO, Virgo, Kagri instruments. Although general relativity successfully explains most known phenomena, its classical black hole solutions contain singularities, and this motivates us to study models in which gravity interacts with additional fields. In this context, regular solutions based on nonlinear electrodynamics avoid singularities, and the dilatonic solution incorporates fundamental dilaton field. The results of my work provide a comparison of these models with classical models of general relativity by analyzing key gravitational effects. Next, I will briefly describe the considered models. 2 of them come from nonlinear electrodynamics coupled to general relativity. The starting point is the action equation 1, where we have a generic Lagrangian depending nonlinearly on the electromagnetic invariant. Varying this action leads to the field equations, and the energy momentum tensor is sourced by nonlinear electromagnetic field. We focus on static spherical symmetric solutions described by metric equation 3, where the mass function is not a constant but is determined by the energy density of the field. Regarding the electromagnetic field itself, in spherical symmetry, we can have two types, radial electric field and radial magnetic field. The first model is van Wank regular black hole. It is defined by this Lagrangian equation 5, which can reproduce other regular solutions, Bardeen and Hayward. The electromagnetic invariant is sourced by a magnetic charge, which is related to the parameter A. The mass function is shown here. As r goes to infinity, it approaches the constant ADM mass. Figure 1 illustrates the horizon structure. There are two horizons which coincide at the critical point marked by a black dot. This is the extremal black hole case. Extremal case corresponds to a maximal possible value of the charge parameter, shown here. A second model is the Debnikova regular black hole. The spacetime is sourced by an electric charge as defined by this Lagrangian equation 8. The basic feature is the theta core at approaching regular center, where the cosmological constant is generated by the energy density of the field. The mass function is shown here, and figure 2 shows the horizon structure. There are also two horizons which coincide at the extremal case with this particular value of the charge parameter. The last model is double-charged dilatonic black hole, which is derived from an action containing two scalar fields and two distinct dilaton coupling vectors. The corresponding static spherical symmetric metric contains moduli function and depends on the extremality parameter mu and on the charge parameter p. The parameter A represents a coupling constant defined by the combination of dilatonic vectors. All the tasks considered in this work are based on the dynamics of test particles. Their motion is governed by the Lagrangian written in the equatorial plane, from which the earlier Lagrange equations are derived. And we should take into account that in the framework of nonlinear electrodynamics, photons don't move along null geodesics of the background geometry, but instead they move along null geodesics of an effective geometry. And the massless particles serve as a reference to describe the net effects. We then move to provisions for defense. Provision 1. In the van Wank regular black hole model, the effects of nonlinear electrodynamics lead to a weakening of gravitational phenomena, including perihelion shift, photon and the massless particles deflection, as the magnetic charge increases. A direct application to observational data for the perihelion shift of S2 star orbiting Sagittarius A star allows us to constrain the magnetic charge to the value 4.34 times to 10 to minus 11 power Webers. We first consider the perihelion shift. From the geodesic equations, we obtain an equation of motion which includes correction due to magnetic charge. To solve it, we apply the perturbation method. The zeroth order term corresponds to the Newtonian orbit, while the perturbative solution yields the relativistic precision. The resulting analytical expression separates two kinds of contributions, the standard GR term and the net induced correction. As shown in figure 3, the perihelion shift decreases with increasing semi-major axis and grows with orbital eccentricity. That is consistent with the relativistic behavior. However, for larger charge, the overall shift becomes smaller. And figure 4 shows the difference between the effects of spacetime geometry and the net on the perihelion shift for given fixed orbital parameters. And for such values, the difference reaches about 32%. An important application is S2 star orbiting Sagittarius A star black hole. Using its known precision and all the parameters listed here, we insert them into our analytical expression, and this yields an upper bound for the magnetic charge, which is 4.34 times to 10 to minus 11 power Webers, which is 4 orders of magnitude is smaller than the Dirac magnetic charge. So this tells us if such net effects exist in the galactic center, the corresponding magnetic charge must be extremely small. We then consider gravitational deflection. The equations of motion are written separately for massless particles and for photons. And to solve them, we again apply the perturbation method. The no-bending approximation corresponds to a straight trajectory, and the perturbative solution yields the deflection. The definition of the total deflection angle is shown here. Here are the resulting analytical expressions for deflection angles for massless particles and photons. And as shown in figure 5, deflection angle decreases with increasing distance of the closest approach, r0, and it is smaller for photons than for massless particles. And figure 6 shows that the relative difference between these two cases grows with charge, and for a given fixed r0, it reaches about 60%. So we can conclude that effects of net are stronger in case of photons and massless particles than in case of massive particles. Revision 2. Accretion disks around the Van Wank and Debnikova regular black holes are characterized by higher differential luminosity than those around the Schwarzschild black hole. The efficiency of converting mass into radiation reaches 11.43% Van Wank and 8.88% Debnikova, exceeding the Schwarzschild value by 2 and 1.5 times respectively. In the binary system Cygnus X1, the maximal possible temperature of a disk surface is 6.70 megakelvin Van Wank and 5.45 megakelvin Debnikova, exceeding value for the Schwarzschild black hole by 1.75 and 1.43 times correspondingly. To analyze the accretion disks, we proceed from the circular motion of neutral massive test particles. The key quantity governing the disk structure is the radius of innermost stable circular orbit, or ISCO. It marks the inner bound of a disk. And in this case, it is derived by equating to zero the second derivative of effective potential. As shown in figure 7, for both Debnikova and Van Wank model, ISCO radius decreases with increasing their charge parameters. Physically, regular core allows stable orbits to extend closer to the horizon. And we can see that Van Wank model permits smallest ISCO radius. Table 1 presents the analytical expressions for angular momentum, energy, and angular velocity of test particles, which we will need later. We use the Novikov-Page-Thorne model, which describes the geometrically thin and the optically thick accretion disk. The energy flux emitted from the disk surface depends on the metric functions and on the orbital characteristics of test particles, and then the differential luminosity can be computed. The temperature distribution follows from the black body approximation, since the radiation emitted from the disk surface is assumed to be in a thermal equilibrium with the matter. Figures 8 and 9 show the flux temperature and differential luminosity for Schwarzschild, Debnikova, and Van Wank black holes. In all cases, these quantities peak near the ISCO, since that's where the matter releases largest fraction of its binding energy. And the ordering of curves is consistent across all panels. So Van Wank model produces highest flux and the temperature, followed by Debnikova. And the Schwarzschild case gives the lowest values. We then apply our results to the well-known binary system Cygnus X1 using the known mass and the known accretion rate. We compute flux and the temperature corresponding to the maximums of their distributions. And for Debnikova black hole, in the extremal case, the computed flux is 4.11 times larger than for Schwarzschild, and the peak temperature reaches about 5.45 megakelvin. For the Van Wank regular black hole, also in the extremal case, the computed flux is about 9.5 times larger than for Schwarzschild, with the peak temperature 6.70 megakelvin. Accretion disks produce very powerful continuous electromagnetic emission known in astrophysics. That's why it is important to compute the efficiency. It quantifies how much of the accretive matter's rest mass is converted into radiation. And as we can see from table 2, For the Dimitrova black hole, in the extremal case, the efficiency reaches about 8.88%. For the Van Wank extremal black hole, the efficiency reaches about 11.43%. When charge parameter, the efficiency when the charge parameters of both models decrease, it becomes smaller. And when both charges vanish, we get the Schwarzschild value 5.72%. So we can say that both regular geometries, in particular Van Wank one, predict substantially more efficient energy release than in the Schwarzschild geometry. Revision 3. For the dilatonic black holes, the radius of innermost stable circular orbit and the efficiency of converting mass into radiation increase monotonically with increasing dilaton coupling parameter A, with the Schwarzschild, Sen, and Reisner-Nordstrom solutions emerging naturally as limiting cases of the theory. The spacetime depends on the extremality and on the charge parameters, which are linked to the gravitational mass and to the net charge. But their explicit form depends on the value of dilaton coupling parameter. In particular, A equal to 0 yields the Schwarzschild solution. A equal to 1 gives the Sen solution, which rises in a string theory. And A equal to 2 gives the Reisner-Nordstrom solution under a suitable radial coordinate transformation. To analyze the properties of spacetime, we derive the expressions for specific energy and the angular momentum of test particles, which are shown in figure 10. The minima of these curves identify the location of ISCO. The ISCO radii can be derived by using one of given equivalent conditions. And the figure 11 shows that shows the dependence of ISCO radii on the net charge for several values of coupling parameter. But both quantities are here normalized by the extremality parameter. However, the trend of ISCO depends on the normalization. And this slide presents the ISCO radii normalized by the gravitational mass and the corresponding radiative efficiency. As shown in left panel of figure 12, as both net charge and the coupling parameter grow, the ISCO radius decreases and the corresponding efficiency rises monotonically. Numerically, the efficiency is again 5.72% for Schwarzschild, 6.5% for Sen case, and 8.14% for the Reisner-Nordstrom case. So stronger dilaton coupling allows more gravitational binding energy to be released in the given spacetime. And this final slide presents the analytical expressions for ISCO radii for three characteristic values of coupling parameter. For A equal to 0, this is exactly Schwarzschild value. For A equal to 1, we obtain an expression which can reproduce the result for the Sen black hole. This can be confirmed graphically in figure 3, taken from the paper by Narziloev et al. This figure presents the dependence of ISCO radii on the net charge of the Sen black hole for charged and neutron test particles. We should compare our red line in the left panel from here with this solid black line, which corresponds to the neutral test particles. And taking into account the relation between the charges of our black hole and the Sen, so our results are completely consistent. And when A equal to 0, our expression after applying an earlier radial coordinate transformation becomes identical to one obtained by Pugliese, Chivetto, and Ruffini for the Reisner-Nordstrom geometry. So these results demonstrate that double charged dilatonic black hole solution naturally contains the Schwarzschild, Sen, and the Reisner-Nordstrom geometries. And finally, let me briefly summarize the outcome of this work. So performed analysis has shown that nonlinear electrodynamics and dilaton coupling modify the structure of spacetime and thus affect the gravitational and radiative processes around black holes. And obtained numerical and analytical results can be used for further observational testing of alternative black hole models. During my doctoral studies, 4 articles were published in journals included in Web of Science and the Scopus databases. 4 articles were published in our local journals, and there is 1 publication in the proceedings of a conference. And that's all. Thank you for your attention.
Any questions? Any comments?
Да. Еще раз.
Any questions, dear colleagues?
Yes, I have one
I
question.
have. Okay.
Please.
Okay, actually in
Go.
calculations, you have like obtained some values of the magnetic charge parameter, let's say L, and you are measuring it in units of Weber. How the magnetic charge is measured in Weber? Actually, this part was quite unclear to me, actually.
Because magnetic charge can be measured in Webers or in ampere multiplied by meters.
We don't hear you. Speak loudly or make microphone close.
Я uzun курс.
Вы можете сюда отвечать.
А сюда отвечать?
Отвечай. Все.
Не получается повторить ответ. So the magnetic charge can be measured in Webers or in amperes multiplied by meter.
Next question.
Okay, my next question is about this
Are you
again. This
satisfied? Okay, next question.
yeah, okay, I am satisfied. Okay, my next question is about the space-time, like fun one, like a space-time.
Да, слышно, они задают уже.
Can I speak?
Yes.
Fun one space-time. Okay, we know that it's regular, as you said, it's regular solution, regular black hole. If L exceeds some like a maximum value, it becomes no horizon space-time. But still after that, it can have some like a ISCO it can have. And if you calculate this, like my question is, have you calculated all the like physical quantities like energy, like efficiency and ISCO radius or like some kind of thermal spectrum you calculated? This all calculated in this no horizon space-time region as well, or only in the black hole you studied?
All these quantities are computed in black hole spacetime before the extremal value of charge parameter.
Okay.
And it's the extremal case.
Okay. Thank you. That's all.
Okay.
Может быть, мне с ноутбуком туда пойти?
Подойди сюда. Не надо подходить.
Можно, да, вопрос?
Да.
Мгм.
Okay.
Смотрите, у вас S2 Star на каком расстоянии находится от Sagittarius A Star?
На влияниях сети.
На английском.
Насколько я знаю, 1000 радиусов Шварцшильда, да? То есть приблизительно.
Ой, да, тысяча.
То есть, смотрите, я смотрел, то есть S2 Star делает один оборот за 16 лет, да? Правильно? Так получается?
Да.
Вы написали 16, я потому что смотрел график. Гульнара?
Да, период 16.
16 лет, да? Смотрите, теперь сколько лет мы наблюдаем это? Может, 30 лет, да? Правильно? Мы всего 1 или 2 оборота увидели, правильно? Теперь, а вот когда мы говорим о перигелии шифта Меркурия, да, это идет за 100 лет сколько-то секунд, правильно? То есть, потому что там за 100 лет делается очень много-много оборотов, статистику можно сделать. Здесь как можно статистику сделать, чтобы наблюдать смещение перигеля S-to-star? Потому что у нас статистики практически два оборота.
Да. Но статистику здесь возможно сделать и методом фитинга. То есть, если на основе того, что у нас имеется, спроецировать будущие возможные положения.
Ага. То есть нам нужно ждать еще 100 лет, чтобы доказать. Ладно, спасибо. Я удовлетворен. Спасибо большое. Хорошо.
Thank you. Next question, please.
Мгм.
Can I ask? Well, can you open page 14?
Page.
Можно вопрос?
А сейчас
Мгм.
Нет, сейчас задает все. Ермак задает, пусть Ермак закончит.
Хорошо, извините.
So here you have massless particles and photons. So what is in difference basically between the massless particles and photons? Because photons are also massless. And so what gives this different values of alpha hat?
This difference arises because of taking into account the nonlinear electrodynamics, since photons, since we introduced the effective geometry to describe the motion of photons. And the massless particles move along geodesics of the background geometry, but for photons we should introduce the effective geometry, and that's why this difference arises.
Okay, so if you have a photon or some other electromagnetic field, well, some other, let's say, like dark photon. So in principle, you can have the usual photon, which would have linear electrodynamics, so Maxwell type, and then you would have nonlinear one, which would describe this black hole solution, for example. Then, so because it's the only difference, then the linear photon, let's call it that, would be the same as massless particle, right? Because, well, that's the only difference that goes into this equation. So you didn't consider spin or anything else, just the well, massless and the type of let's say Lagrangian.
Oh no, we didn't consider this.
Okay, so so basically, if you would have a linear electrodynamics, the Maxwell electrodynamics, these two equations would be the same, correct?
Yes.
Okay, thank you.
Thank you. Next question, please.
Mhm. I have such question. It is well known that Schwarzschild metric is stable, but stability for Kerr metric is proved only for very little values of rotation parameter. What you can say about stability of main metrics we used in your investigation and application to astrophysics, please?
In previous work, it was shown that Van Wank and Debnikova metrics are stable under the axial perturbations of test scalar field. So they're stable, non-rotating analogs. And the thermodynamical stability was also investigated for the double-charged telatonic black hole. But when it comes to rotational analogs, so for example, there are problems for the Van Wank black hole.
Okay. Thermodynamic stability, that's enough for astrophysical application in particular. Thank you.
Thank you.
Thank you. Any more questions? No questions. Okay.
Everything is clear. We had a lot of discussions.
If, okay. If possible, I should like comment activity of Suliyeva Gulnara in
Discussion will be later.
No, discussion later. Now,
yes. Discussion later. Okay.
If you have no
Гульнара, мы можем, наверное, смотрите, вот выбор модели аккреционного диска, чем был обусловлен? Вот такой вопрос.
Вот мы использовали модель Новикова-Пейджа-Торна. Например, существуют другие модели, например, бонд-аккреция или там нерелятивистское приближение, но именно вот модель Новикова-Пейджа-Торна, она как бы, этот механизм позволяет получить более высокую эффективность преобразования массового излучения и более высокие светимости. И при этом она как раз позволяет рассматривать круговое движение пробных частиц, что упрощает анализ.
Спасибо, я удовлетворен.
Okay. If you have no other questions, the next floor will be given to scientific supervisor Kontai Bushkayev.
Okay, thank you. The work of Gulnara is interesting because we have a lot of black hole candidates, including supermassive black holes at the centers of galaxies, including stellar mass black holes.
Гульнара, презентацию выключите, будет легче. Мы будем видеть целый экран.
And so today, the main question is, do we have enough observational evidences to support different theories of black holes, like if the black holes are singular black holes or they are regular black holes? And I think it is still an open issue because using data from Event Horizon Telescope and using data also for supermassive black holes at the centers of galaxies like redshift and so on, it is really hard to distinguish or to rule out different theories of gravity. So using different theories of gravity, you can explain all the observational evidences that we have so far from astrophysics related to black holes. So you can use 10 black hole solution, you can use one black hole solution, and you can still explain most of the observational data. So the work of Gulnara mainly focused on singular and regular black hole solutions, and she just wanted to check if we can calculate accretion disk properties, also if we can calculate the emission or conversion of matter into radiation. Initially, we just wanted to see which of the regular black hole solution give us the maximum emission rate, because we just wanted to see what kind of, for example, regular black hole solution will give us smaller ISCO and correspondingly will give us a larger emission rate and larger conversion of matter into radiation. So we tested several regular black hole solutions, and in the end, we showed that one is the thickest one, and at the same time, it can give us most ISCO radius and the highest conversion of into radiation. Of course, in the future, we would like to expand this work, including rotation, including different particles, spinning particles. Maybe we can also consider the effect of dark matter around regular and singular black holes, just to see if we can have some observational data in order to check our outcomes. I think Gulnara within this 3 years completed all her assigned tasks, so she did a good job. And in my case, I just want to support her, and I also call you to support Gulnara for being active, for being diligent and dedicated PhD student. So dissertation work, series of articles fully meets the requirements for PhD thesis established by the Ministry of Science and Higher Education of the Republic of Kazakhstan. And I therefore recommend that Dissertation Council award her the degree of Doctor of Philosophy, PhD in Educational Program 8D05306 Physics. So, thank you.
Thank you. The following is a review from a foreign scientific supervisor, PhD professor at the University of Camerina, Orlando Luongo.
Thank you. Let's read the review from the professor, foreign professor, scientific consultant for the doctoral student, our Suliyeva Gulnara. Review on the PhD thesis, application of field theories to the astrophysical problems by Suliyeva Gulnara, Department Theoretical and Nuclear Physics, Al-Farabi, Kazakh National University. The research work of Gulnara Suliyeva is devoted to the study of black hole models arising in the modified theories of gravity, where additional fields, scalar, vector, and the non-linear electromagnetic are included into the structure of space-time. The work aims to identify deviations from classical general relativity predictions that could, in the principle, be the subject of observational verifications. In summary, the research of Gulnara Suliyeva represents an attempt to apply field theoretical models to the astrophysical black hole problems. The candidate demonstrates familiarity with the modern approaches in gravitational physics, is capable of performing analytical and numerical calculations, and has produced a number of results that expand upon classical GR solutions. The research work contains results of scientific work. Therefore, I consider that it corresponds to the standards required for award of the degree of Doctor of Philosophy in Physics. Scientific Supervisor Professor Orlando Luongo, School of Science and Technology, Physics Division, Camerina, Italy.
Thank you. Thank you. Now let's get to the discussion or review. The floor is now
Review,
given.
yes.
Review. Нет, review. The floor is now given to the official reviewers. Academician Ahmedov Bulbomurod.
Okay. Thank you very much for giving me opportunity to speak here. So it is my review on the work by Gulnara Suliyeva, who submitted her research work on the title Application of Field Theories to Astrophysical Problems for getting degree of Doctor of Philosophy in Physics. So I would like to say that we live now in the era of mimicry and degeneracy of the black hole parameters. And from this point of view, the work which is done by Gulnara Suliyeva is very important because he is working on this direction. So it is from topicality and from the performance, it is in the highly relevant to the current tendencies in the relativistic astrophysics. And then I would like to mention that this work is performed in the framework of the projects of the Kazakh national agency, which is also very important. And in total, the work is performed in very high level because papers were published in the referred journals. 4 papers are published in the highly referred journals. So we know that these papers pass through the serious reviewer process. So this is very important. And finally, I would like to say that the research work by Suliyeva titled Application of Field Theories to Astrophysical Problems meets all the standards established by the Committee of Quality Assistance in Science and Higher Education of the Republic of Kazakhstan for awarding the degree of Doctor of Philosophy. And Suliyeva Gulnara herself is deserving of being awarded the academic degree of Doctor of Philosophy in Physics. So I kindly request all members of the Science Council to vote for this for getting this degree. And from my point of view, all results are very important, and there is a lot of work can be done by Gulnara Suliyeva in the future. Thank you. If you have questions, you can ask me.
No question. Thank you.
Hello.
The second
Okay, thank you very much.
The second reviewer is Aldabergenov Yermek, PhD Research Associate of Fudan University, China.
Thank you. So I would like to mention and agree with Professor Akhmedov and mention that the work done by Gulnara meets all the standards and criteria established by the Committee for Quality Assurance in Science and Higher Education of the Republic of Kazakhstan. The work is interesting. The results are new, based on the publications, on the work, the results that Gulnara explained in her presentation. Based on this and on some personal correspondence regarding the research project, I can say from my side that Gulnara understands this area of research and the results and methods, and did the substantial work regarding the motion of test particles, accretion disks, and various effects, the black hole models, such as the regular black holes with in nonlinear electrodynamics and the dilatonic black holes. So I'm happy to recommend awarding the degree of Doctor of Philosophy to Gulnara in the area in physics. Yeah, that's all from my side. Thank you.
Thank you. Dear colleagues, each of the official reviewers has provided their review. And now the floor is now given to the final word of the PhD candidate Gulnara Suliyeva.
I'm grateful to everyone who has attended today. I'm very grateful also to my supervisors for
There were
their
some
help.
people for discussion, I think. Some professor wanted to say something.
After this final
Yeah.
word.
Okay. In Uzbekistan, this dissertant speaks the last one. Candidate is the last one here in Uzbekistan, but in Kazakhstan, maybe different rules. Okay.
Colleagues, discussion will be later.
So
Okay. Good.
grateful to
I should like I should like to note that in collaboration with Laboratory of Cosmology and Gravitation in Astrophysical Institute in Almaty, we should know that the a few days ago, yet one paper in International Journal of Modern Physics was published on the problem of traversal wormholes and origin of scalar background. Soon we can see it is in print now. We should note that cooperation with Gulnara Suliyeva in our laboratory, we should note her very high level in treatment, physical treatment, and mathematical processing, data processing of different results, astrophysical. What such comment from Astrophysical Institute, Фисенков Astrophysical Institute in Kazakhstan. That's all.
Okay, thank you. Let's continue the discussion. Who would like to speak?
I wanted to say something, if you do not mind.
Okay.
So regarding the work, it is very interesting because the regularization of the space-time and in principle the effect of the nonlinear electrodynamics to the space-time properties and through the space-time changed it is affecting to this some astrophysical processes is very important, and that's why the works of Suliyeva Gulnara is very important and making a lot of contribution to this very hot research area. So that's why I would like to mention that these work are very good, that has very good results and giving very good contribution to this area. On the other hand, I would like to mention that Suliyeva Gulnara is very actively participating in conference. I have heard her presentation in conference in Kazakhstan and in Uzbekistan several times, and every time her presentation was very in an excellent way. So that's why I strongly support this work, and I also kindly ask other participants of this council also to support this work.
Okay, thank you. Any remarks? Once more.
In total, if you want, I can say about tendency, which we have here during the last years. So, what may I speak, talk? May I discuss?
Yes, you can.
Yeah. What we see tendency in Al-Farabi University or in Nazarbayev University, and there is Euro-Asian University. In all of them, there is growing interest of female PhD students to the relativistic astrophysics. So from this point of view, Gulnara Suliyeva is not the exception, and we are very happy that you have now big army of female young researchers who are doing a very excellent job in relativistic astrophysics. It is really good tendency. So please keep it, and I think this Gulnara Suliyeva also will work on this direction, and we will have more professors, very highly qualified professors in relativistic astrophysics in Kazakhstan very soon. So I would like to to wish great success. And then what we see is this Kuantay Bashkayev. So he's constructing very good research team, and I think this research team is becoming well known on the in the world. From this point of view, I support this. Okay, somebody is calling, so I support this difference.
Okay, thank you.
Yes. Okay, come. What's you do something? There is PhD defense, but it.
Sure. We move on to the next stage of the council meeting. For the secret ballot, the floor is now given to Academic Secretary Kunduz Turikhanova.
Thank you. Dear members of Dissertation Council, a ballot for secret voting has been sent to your email address. Could you check your email and vote, please?
Vote, да, сейчас?
Yes, yeah.
Ахмаджан, вы отправили, да, или?
Yes, we sent.
Okay.
Yeah, we sent vote link for your emails. Please, could you check?
Okay.
Видно, да?
Да, видно. Может, там стоит.
Я ничего не получил. I did not receive, so maybe.
Ой, последний.
I think it is my.
Promo-акции пусть.
Ahmadjan, siz oldingizmi?
Aqani o'chirib turasiz. VPN'ni o'chirib, pochtangizni tekshirib, keyin VPN'ni yoqasiz.
Endi men qaysi pochtani berganman, o'shani bilmayapman-da. Agarda Astrinni o'shanda-da problema. На какой адрес вы мне отправляете?
Ахмедов Астрин. Ахмедов Астрин.
Да, все, я получил.
Я да,
Есть, постойте. Все, есть. Так, прикольно.
Я проголосовал, Абдужаббар.
Ahmadjon country ichida yotibdi, yana kiraymi VPNga? Yana kirish kerakmi VPNga? Yana qaytadan kirish kerak. Vaqti. Целый naqa ekan-ku. I voted.
Okay. Okay, thank you.
To announce the results of the secret ballot, the floor is given to the scientific secretary.
Altıyer. Bu kadar şey yapmayı. Screen. This one. Okay. Okay, thank you. Do you see my screen?
Yeah.
Yeah. Okay. Thank you so much for voting. And now let's allow the result of the secret vote to be published. All the members of dissertation council voted. The results, as you see, the results are given by electronic Excel document, and the award of academic degree of Doctor of Philosophy is 8, and the referral of dissertation for review 0, referral of the dissertation for defense 0, refusal to award the degree of Doctor of Philosophy PhD or Doctor of Science in the field 0.
Thank you. Within the framework of the dissertation council for specialties, physics, technical physics, physics and astronomy, material science and technology of new materials, thermal power engineering, electric power engineering, physics, standardization and certification, nuclear medicine, radio engineering, electronics and telecommunications at Al-Farabi Kazakh National University, to award Gulnara Suliyeva the degree of Doctor of Philosophy in the educational program 8D05306 Physics. Congratulations.
Congratulations. Very good.
According to the regulations, we need to accept the conclusions of Dissertation Council on the dissertation series of articles of Gulnara Suliyeva. The conclusion and classification criteria for the dissertation have been mailed to all Dissertation Council members. Do you have any comments or suggestions?
You can use it.
Yeah. It is all right.
No comment.
Okay, it is proposed to take this as a basis. At this point, the meeting of the Dissertation Council for the defense of the dissertation series of articles of Gulnara Suliyeva is declared closed. Thank you very much.
Thank you so much for participation, for support,
Thank you.
everyone.
Good luck.
Thank you.
Thank you. Congratulations
Bye.
to
Congratulations.
Congratulations. Gulnara, congratulations.
Thank
We
you.
are very happy for you. Okay.
Thank you.
We are happy
Thank
for
you so much.
Yeah, okay.
Uh,
Bye.
You may now celebrate.
All right.